Welcome, everyone. Today we're going to talk about customer loads and transformer protection. So last week we started talking about expulsion fuses, how they operate, how they interact with faults, what they do for us in our distribution system. And we talked a little bit about the wire we use and the cable and the characteristics of that and how they are imperfect and have impedance. And then under fault conditions, that's a darn fine thing because that impedance on those cables is the only thing limiting the current flow from our sources. So from an equipment protection perspective, we want the fastest, shortest operating, quickest to go fuses you can get your hands on. We want to make sure that as little energy as possible flows into that faulted condition because that's going to be contributing to arcing, and that arcing is going to result in, that very hot arc is going to be doing damage to our equipment, melting things down, setting things on fire, very highly destructive. So we want to interrupt that as fast as we possibly can. And so, from an equipment protection perspective, it'd be really great if we didn't ever have any load current, right? We'd like things to go as fast as we can possibly make them go. And as soon as there's any sort of current flowing, just put the brakes to it. But if we did that, we wouldn't have a very useful distribution system. So, we stand by the principle we want to operate as fast as possible, but what really defines fast as possible? And that is our customer loads. So, we do have customers attached to our system, and they are going to be drawing current, which means we're going to have energy flows. Some of those customers are going to be industrials who have great big motors that they're going to be starting, not always in the gentlest fashion, and we're going to see these temporary overloads that will appear on our system and then disappear. And so we have to be able to adjust our protection, our fusing, to make sure that it's sensitive enough that it can detect a fault, but not so sensitive that it's going to operate during these very normal, routine, run-of-the-mill sort of events. And so we're going to spend a little time talking about customers and their performance and the things that they do for us. Now, it's important to note that all of our fusing that we're going to be talking about in this course is all located on the primary side. So whenever we're talking about currents, they're always referenced to the primary side of the transformer. We won't be doing anything, although we talk about load on the secondary side of the transformer, all of our math, all of our currents, all of our everythings is always referenced to the high side. So let's start out taking a look at the physical construction of a distribution transformer. And I know you guys have a course on transformers, but bear with me for a minute here because we're going to be talking about distribution transformers strictly from the sense of how they contribute and how protection works. So our basic structure on our distribution transformer, we've got a transformer core. So this is made out of laminated layers of steel, all made into a stack. So you get a core, and then you stack another one on top of it, and another one on top of it, and another one on top of it, and another one on top of it, till you got a nice beefy core laid up. And the thinner the sheets of metal you use to do that, within reason, the less eddy currents and the higher performance you can get out of your transformer with less losses. So, a stack of thin sheets of steel to make up this transformer core. And in practice, most transformer cores are going to be a little more advanced than this in their construction, but fundamentally they all work the same way. So we're going to start out with a transformer core made out of some sort of highly conductive steel, or it's not the electrical conductivity we care about, it's the magnetic conductivity that we care about. And we're going to take that piece of steel and we're going to wrap our primary coil of wire around it. And we're going to wrap our secondary coil of wire around it. And between the two of those, we know that we can get a ratio on our output voltage, right? So if we have a 10-to-1 ratio, we can adjust our primary to our secondary coil voltage by a factor of 10. But let's pause for just a moment here because there's a little bit of a concerning thing going on. We talked about trans faults last week, and a fault occurs whenever you have your primary line and it connects either to another primary line or gets tied to neutral or ground. So anytime you take a piece of wire and you hook it up from your primary side to your ground or your neutral, um, that's a short circuit. We saw what happened when we got short circuits. The current went to the moon. Um, so what is about transformers that are special? Obviously, we know we can hook transformers up. We see them all the time. Our system isn't constantly on fire, so there's something special going on here with that transformer. What is it? And the magic is in the core. And what we see here is that a transformer is a electricity converter. So it converts energy from electrical energy into magnetic energy. So we have electrical energy flowing here. And remember in the earlier lessons, I said whenever you have electricity flowing, you have magnetism. So that coil of wire that is our primary coil forms an electromagnet, and it starts to transfer that electrical energy into a circulating magnetic field. And then on the secondary side, whenever you have electricity, you have magnetism. The reverse is also true. Whenever you have flowing magnetism, you have electricity. And so on the secondary side, so we get this flow of magnetic energy going around the transformer core, being pulled, and that flow is being triggered by the energy in the primary side. And it's going to flow, and it's going to flow through here, and it's going to induce a voltage on our secondary terminals. And so the transformer core sort of acts as a tank. If you think about this like a water tank, really, right? So you could have like a 4-inch main coming in, and you got a great big storage tank full of water, and then maybe you've got a 1-inch, uh, feed line coming out of that tank. And so when the tank is empty, that line is going to be flowing like crazy. So when there isn't that magnetic circuit set up, yeah, this coil does look a lot like a short circuit. Really, really high currents are going to flow. But much like our water tank, if you're not taking water out of the tank, eventually the tank gets full, and then the pressure inside the tank starts to rise, and eventually the pressure inside the tank and the pressure in your supply are equal, and the water stops flowing into your tank. And the only time you get more water into your tank is if you take some out, or if your tank has a leak in it. The water will flow in to just replace what's leaving. And so we get the same thing happening in our transformers. We get energy coming in through the primary side. We convert that into our magnetic energy. And this magnetic energy here, if we're not drawing that energy back out on the secondary side, begins to create a back pressure. And that back pressure, which is called a back EMF or a back electromagnetic force, it's a voltage that opposes the primary voltage. And what ends up happening is if we're not taking any energy out of this side, this magnetic core, the tank, if you will, fills up and starts pushing back. It creates a back pressure, and eventually we don't get any more energy flow. So if we don't have energy flow, if we have a voltage but no energy, what do we not have? No current. So because of that back EMF, the effective voltage across these coils starts to drop and drop and drop because of this back EMF that's present. And eventually the voltage across the coil is effectively zero. The only, well, I mean, transformers are real things, so there's always a little losses. It's kind of like you got a tiny hole in your tank. a little trickle, so there's a little bit of water moving. You get a little bit of energy flowing into it from losses, but outside of that, you're not going to see any energy flowing. And that's why our transformers don't act like short circuits under normal circumstances. And this is true all the time, except if you have, there's two scenarios where this isn't really true. And the first of those is if you get a fault on the secondary side of the transformer. If you get a fault here, all of the sudden, the energy flows out as fast as it flows in. This is like having a breach in your tank. And now all of a sudden there's no back EMF. This is going to suck energy into it and across that core as fast as it's able to try and feed that fault over here. And you'll see that as a fault-like energy flow, current flow on the primary side. The other case where you'll see that magnetic tank doesn't fill up is if the power was off. In order for that magnetic current to persist, there needs to be a flow of electricity available to it. As soon as you turn the power off, within the tiniest fraction of a second, that magnetic tank is empty. It's not really, unlike a water tank, which stays full till you drain it, these magnetic tanks only stay full while the voltage is still applied. As soon as you turn the power off, gone. So if we're in an outage condition and we turn the power back on, for a tiny fraction of a second, for the first cycle or so, that magnetic back pressure isn't present, and that coil looks an awful lot like a short circuit. And what we're going to see is a tremendously large flow of current during the first tenth of a second as that magnetic field gets set up. And so if you've got a circuit out, you flip the power on for the first tenth of a second, huge flow of current is going to flow as you go and you set up magnetic back pressure, fill those magnetic tanks in all the connected transformers. And so you get this temporary, very high overload current that flows, only lasts a tenth of a second, and that's known as a hot load inrush or a hot load pickup condition. Now, there's a second thing that's, so when we're setting up our fusing, we got to make sure that our fuses aren't so sensitive that they confuse the high currents associated with a hot load inrush with a fault, because that would result in our fuse tripping whenever we tried to turn the power back on. Obviously no good. Second thing we got to look out for is a thing known as load diversity. So when a utility is connecting its customers, you might have a 200 amp service in your house. If your house is older, it might be a 100 amp service. That doesn't mean that your house is always flowing 100 or 200 amps. Most 200 amp services never come anywhere near flowing 200 amps continuously. And so as a utility, it would be incredibly wasteful and very expensive if we were to say, okay, we've got 4 houses, 200 amps each. I need transformation that can handle 800 amps. That's not how it works when we're sizing our equipment. That would be incredibly expensive and honestly very wasteful, because we know that it's likely those houses would never hit their 200 amps that the service would support. And even if they did, be incredibly unlikely that they'd all hit it at the same time. I mean, what we do is we see this averaging effect. So if you have 5 houses, at the first house, it's the morning, someone gets up, they turn on the shower, their hot water heater comes on. Someone else is just getting out of the shower, the hot water heater turns off. Somebody starts making breakfast, they flip on the toaster, someone else is leaving for work, so they shut off the TV and all the lights, and you get all this averaging effect where things are coming on, but other things are turning off, right? Toaster's kicking off just as someone else is turning their kettle on. You get this smoothing effect that happens. And so you don't see these super high peaks that you might expect if all you were doing is looking at how much equipment was connected. So load diversity works really well. And there's a couple notable exceptions where load diversity falls off. Um, One of them, of course, major public events. So, for example, at the first commercial break in the Super Bowl, every major city in the North America, in the football watching parts of North America, their water systems all make sure the water towers are topped off before the first commercial break comes on the Super Bowl. And they make sure that their sewage treatment plants have all their lagoons nice and low before the first commercial break at the Super Bowl. Because what happens at the first commercial break of the Super Bowl? Millions of people go to the washroom and they all flush the toilet at once. And suddenly there's this tremendous demand for water. The water pressure drops all throughout the city as everyone simultaneously flushes. In England, Downton Abbey, which is a very popular TV show there, their Christmas special every year, the agency in charge of the electrical grid posts a guy, and his job is to watch the Downton Abbey Christmas special because he knows that at the first commercial break, there's going to be about a 400 megawatt surge. That's like half a nuclear reactor of electrical energy demand that just appears out of nowhere and lasts about 3 minutes. And that's 400 megawatts worth of British tea kettles coming on all at once as families across the country step away from watching their show and turn on the kettle to make a cup of tea. So, whenever you get this spot where everybody acts at once, you lose your load diversity. The one that we're most concerned with isn't TV shows and it's not major sporting events, it's power outages. Imagine, if you will, that we have a power outage and it lasts a long time. Maybe it's been 4 hours, maybe it's been six. It's the end of July. It's hot, it's humid, and you've been without power for 6 hours through the heat of the day. And the power kicks back on. You're grateful, and what happens? Your air conditioner kicks on immediately because your house is hot. Your fridge kicks on immediately because the fridge is warm. Your freezer kicks on immediately because it's not cool enough either. Your lights kick on immediately. Your pool pump, if you've got one, kicks on because it should have been running and it knows it hasn't been. And it's not just in your house that everything kicks on. All your neighbors' houses kick on everything all at once as well. And so all of a sudden, this assumption that we have that, oh, we don't need a great big transformer because nobody's going to use that much transformation all at once. Well, that assumption breaks down whenever you have a restoration from a power outage. And you get this massive overload, and it lasts quite a while. It could last, it'll be an hour or sometimes 2 hours before you finish getting everything cycling back down. But really, you see in the first, 900 seconds or so, the first 15 minutes, things start to settle down. People's fridges and freezers start to kick off and then back on again. People's water heaters settle down. People's air conditioners start cycling in and out again, and things start getting back to normal within a couple of minutes. And then, it might be an hour before, maybe 2 hours if it was a really bad one, before things really finish getting back into their groove and everything's back to normal. And so when we're setting up our fusing, we need to make sure that it can accommodate, again, these temporary overloads, because that's a very normal thing, right? You're going to see a lot of energy flowing into those homes which are very hungry for energy when they haven't had any for a while and we've got extreme weather. Nothing's wrong. That's entirely normal. We don't want our fusing to be operated under these conditions. So this creates a second limitation we got to deal with. This is called cold load pickup or cold load inrush, and it lasts from the edge of hot load inrush, so from about a tenth of a second out to, we call it 900 seconds or so. So if we combine these two, what we end up with is a lower boundary, right? A line, a set of conditions where you do not want your fuse to operate underneath this level. right? Whatever fuse you pick to protect that transformer or that set of lateral and that set of customers, it cannot go operate underneath this inrush boundary. And the multipliers have been determined for the most part empirically. So these are not, you know, numbers that were generated by a scientist in a laboratory. These are numbers that have been generated by utilities ourselves by measuring the current flows over years and years and years of experience. And these are the numbers that have been come to be accepted as the standard values. And so in that hot load inrush period, right, when we're setting up those magnetic tanks, we see 25 times per unit. And so per unit is multiples of the rated current flow. So if you have a transformer and 100% of its rating is 10 amps, that means for the first hundredth of a second, you're not seeing 10 amps flow through that transformer, you're seeing 250. A tenth of a second after power is on, that 250 amps is now dropped to 120, but you're still putting 120 amps through a transformer that's only designed for 10. That's pretty intense. Now, at the end of this period here, all that magnetic back EMF, those magnetic tanks, they're all established. The transformer's now operating. It's doing its normal thing. Everything we see from here and down, this is loss of load diversity that we're dealing with. And after 1 second, we could be seeing 6 times the full load rating of that transformer flowing in energy and current flowing through that. Our 10 amp transformer, 1 second in, still flowing 60 amps. That's pretty intense. By the time we hit 10 seconds, things start to stabilize. Because it's not just our equipment that's got magnetic fields and power supplies. Think of how many power supplies you have plugged into the wall at your house. TVs and car chargers or phone chargers and video game consoles and microwaves, anything with a clock on it, it's always got a power supply. It's always turned on. It's never really off. And so when we establish that our transformer starts working, now electricity is available to our customers. Now all those little power supplies need to get their magnetic fields set up, and that takes another fraction of a second. By the time we get out to 10 seconds, we see that we're dropped to 33, a multiplier of 3. So our little 10 amp transformer is now only flowing 30 amps, which if you're comfortable with that, you shouldn't be. You shouldn't be flowing 30 amps through something that says I'm only good for 10. By the time you get out to 900 seconds, we're 15 minutes out, we still might be seeing 20 amps flowing through our transformer only rated for 10. And then at some point beyond that, we're going to trickle back down to whatever our nominal load was. So per unit, this is multiples of our full load rating. And so you can see these inrush values, these things are intense. And so our fusing has to be permissive enough to allow it, but also our transformers have to be robust enough that they can take these kind of short-term overloads without being damaged. So let's do an example. For example, what would the inrush limit be for a 50 kVA, very common transformer, fed 16,000 volts? Well, our first step is we have to figure out what our full load amps is. So what's our full load current? We can do this by taking our 50 kVA, put it over 16, K cancels with K, V cancels with V, we're left with A. We know we did it right, yay for unit analysis, and we get 3 1/8 amps. Now, be careful with your units. It's fine to divide kVA by kV, but you wouldn't want to divide kVA by V. You'd be off by a factor of 1,000. You'd get kind of a strange number. I like doing it the unit analysis way. Make sure that things don't go off the rails. I may ask you this question with mixed units, so please pay attention. Either make sure that everything finds its way into base units, so 50,000 VA over 16,000 volts, or make sure everything is in kilounits, 50 kVA over 16 kV. Doesn't matter, but you have to be consistent or your math will blow up. So once we have our full load amps for this transformer, we can go to our table. So we write it out, all our times, what our multipliers are for our inrush. Again, we've got our our hot and our cold load inrushes. And we're going to take those and we're going to multiply each line by our full load amps. And we find out that our 3 amp transformer, 1/100th of a second after being energized, is potentially flowing just under 80 amps. And we can see as that's going to taper off as time goes. So we know what sort of abuse our transformers might be tolerating at the end of a power outage. And we know that obviously our fusing has to be hot, tolerant enough that it would allow this to occur without the fuse operating. But it does lead to the question, well, if a 3 amp transformer can take almost an 80 amp surge, how much more can it take? Like, really, how tough are these things before you damage your transformer? And again, it's back to standards. It's the IEEE. So in Canada, we use an IEEE standard for transformers. We liked it a lot, so we put a Canadian Standards Association number on it, and it's the same thing. And we divide our transformers into categories. And we're going to focus in this class on category 1 transformers because, 0 to 500 kVA single phase or 15 to 500 kVA on a three phase, that covers the lion's share of your pole mount. It covers all your pole mounted transformers, and it covers the lion's share of pad mount transformers that you're going to find in everything except industrial sites. As linemen, these are the transformers that you're going to be working with day in and day out. So we're going to restrict our course to focusing on the category 1 transformers because these are going to be the most relevant to us. So the enemy of transformers, the number one enemy is heat, right? So what kills a transformer? Insulation failure. What kills insulation? Getting it too hot. Now, under fault conditions, there is a second thing that goes on. Those very high current flows that we're seeing, well, when you have magnetism, if you've ever held magnets together, tried to force two North Pole magnets together or pull apart a North and a South Pole magnet, there's a physical force there. Magnetism tries to move things. And so the other thing that is happening here, other than heat, and thankfully our transformers are these bulky, things made out of steel, so it's going to take more than a little bit of heat to actually warm the thing up, which in this case works greatly to our benefit. But the other thing that happens under high current flow conditions, and this is more of a problem under faults than it is under inrush, is that as the current goes up, the magnetic forces also go up. And so you get this force, and it's literally the coils start squeezing around the core. And if they're not properly braced, the coil itself will literally crush down on the insulation that protects it, and the transformer can crush itself to death. I have seen failed transformers where you open up the tank and the lead coming off the bushing goes through a support bracket and the bracket's been ripped off. I have seen bus bar in our substation, which was, imagine a 6-inch tall, quarter-inch thick bar of copper bolted down with half-inch or three-quarter-inch bolts to hold it all in place. And I have seen that ripped right off where the bars had then contacted and welded themselves together because of the magnetic forces involved from the very high currents at a fault. So these physical forces, this magnetic force that is trying to crush and rip and tear our stuff, can be pretty significant under fault conditions. And so the standards that these transformers have to be built to, they have to account for both of those things. They have to account for heating, like did we flow so much energy through this that the tiny little connectors where our lugs are attached melted off? But also, is the bracing internally robust enough? Is it tough enough that when this fault current puts the squeeze on it, it's not going to twist itself into a pretzel and not work anymore? So the fine folks at the IEEE, mostly being engineers and scientists, instead of going with empirical values for this, they decided we were going to use an equation. And the equation that they came up to is T equals 1250 over I squared. So here, T is time in seconds, and I is current per unit. Again, a multiplier of whatever transformer you're dealing with. Whatever its full load current rating is, this gets to be a multiplier value. So this is great if we know I. We know this formula in its current form. If we know our I, how many multiples of full load current you're exposing this transformer to, it will pop out a T. So if you're experiencing 25 times your full load current, I would expect you could solve the equation, T seconds before your transformer might suffer damage. Pretty cool, but let's reorganize that equation. We flip it around, and now we can say, for a given time, how much current can it withstand? If we express it this way, we can build a table that looks an awful lot like our Inrush table. And so let's do that. We can take our rearranged equation, and we can build out a set of multipliers. And these multipliers come from plugging our different T's in here. All right, we're going to take our T, we're going to plug it in here, and an I is going to pop out, and we'll put it there. So we can build out a table. Now, it's important to note there is one difference in these tables. With Inrush, we went out to 900 seconds. The IEEE guys, being scientists and engineers, decided they liked multiples of 10, and this only goes out to 100 seconds. So there's a little bit of a difference. And the standard actually says after 100 seconds, all bets are off. So we have to use 100 seconds as our upper time scale. We're not obligated to use these exact times, but they are convenient. They're very easy to plot on a log-log graph. And if we plot 5 points, that's enough to make us a very nice little line that's pretty easy to draw and easy to understand how it follows. So I like setting the table up like this, and then we can calculate out our multipliers. If you really don't like math, as long as you use these times, you always end up with these multipliers. So pick your poison. You can calculate them on demand, or you can memorize this set, and it'll be enough to keep you rolling through this course. So what we can do is then we're able to take our full load amps, multiply it out, and what we end up with is really two sets of lines. We end up with a line that is our inrush curve. And if you plot the points from the inrush curve on a log-log graph, it makes a mostly straight line. And we know that anything on this side, so anything less than our inrush curve, this represents our normal operating region, right? Everything's hunky-dory as long as you're not above the inrush line. The inrush line is what we define as the upper bounds of normal operation. If you're under inrush, everything's good. If you're over inrush, things are bad. Operate your fuse. And then we have another line. And if you take this equation and you pick some times and plot it out in a log-log graph, this also gives you a very nice straight line. And so this is the boundary where if you are above that, you've probably cooked your transformer, which is unfortunate because they're expensive and difficult to replace and take potentially 16 weeks to show up on your doorstep from when you order them. So you don't want to be blowing up transformers if you can at all help it. Really, that's the point of putting a fuse on it. So you blow the fuse, which is inexpensive and easy to come by, rather than the transformer, which is expensive and not. So we end up with two lines. We get our inrush line, this is our normal region, and we get our transformer damage curve. You cross the curve, you've cooked your transformer. You don't cross the curve, it's expected your transformer is going to survive. Doesn't always happen. These things can't take an infinite number of hits right up against the edge of the line before they let go. But the expectation is, and for the purposes of our course and the development of fuse protection, as long as you stay under the damage curve line, the transformer should survive unharmed. And what you get is this margin in between. And if we can drop a fuse that fits in between here, then we can interrupt the flow of electricity only when it's above the inrush, but while it stays below the transformer damage curve. And this is kind of what we're hoping to achieve. We want to stay away. We don't want our fuse to operate when we're in our normal region, and we want our fuse to finish operating before we cook our transformer. And so what we want to do is we want to pick a fuse that rides in between these lines and protects our assets without causing nuisance trips and leaving our customers in the dark for nothing, and without allowing our transformer to blow itself up. Let's do an example. Let's go with a 100 kVA transformer this time. First step, figure out our full load amps. Second step, build our inrush table, just like we did before. We have our multipliers. There is no magic. You should just write these down and keep it someplace handy. If this wasn't a remote course, my test would be closed book and I'd make you memorize it. So you build your inrush table and you multiply everything by your full load amps, and out comes your inrush currents expressed as amps. And then we're going to build our um, transformer damage line. So we have our times. Again, keep a note, 900, 100, not the same. We plug those times into our formula because the IEEE is full of engineers and scientists and they love formulas, and we end up with our multipliers. We multiply by our full load amps, and out pops our damage current thresholds for each of those times. Now what we can do is we can take a set of a fuse series. So in this case, these are all of our T-speed fuses. One of the two series of fuses we covered at our introduction last week. I said we were going to do K-speed fuses, which were our fast fuses, and T-speed fuses, which were our slow. And I've kind of arbitrarily picked the T-speed fuses. What we can do is we can plot those 10 points that we built on our tables, here and here, onto our graph. So we're going to put our inrush, which I drew in blue, right? So we see inrush time 0.01 seconds, 2,210 amps. So we're going to go to 0.01 seconds, 1,000, 1,000, 2,000. I made a mistake. 2,000 amps, 2,200 amps, and then at a tenth of a second, we're at 699. We'll call that 700 because I can't draw that well. So 1/10 of a second is here, and so we go 1,000, 900, 800, 700. And let's clean up our line here. So we're able to draw those points. We get our line. Then we're going to do the exact same thing with our damage curve lines. So what have I done? Yeah, I'm reading the wrong thing. That wasn't wrong at all. Maybe I can find a way to edit that out. 156, 100, about 150, near the 75% marker, and 75, 90, 80, 75. Straight line, which is always a good sign. There we go. Put back the way she was. Now we can go back. We can plot our points for our damage curve. This time I did it in red. So we plot our points. And what we see is that some of our fuses, so the 6T, for example, would not be a good candidate fuse. It operates on the left side of the inrush line. So we could be at, for example, 20 seconds, and we could be at 15 amps, and that puts us right about here. And it's very possible that we operate our fuse before we hit our boundary. So we could have an inrush condition that put us right here and our fuse tripped. And now our customers are in the dark. Why are they in the dark? Nothing broke. There was no fault. You're going to get there as the lineman on call, and you're going to patrol the line, and you're going to say, I don't see anything wrong. I wonder what happened. And now you're in the awkward spot of, do you keep searching, or do you put another fuse in and just hope that the problem has gone away? So the 6T fuse, a little bit too small. You take a look at something like the 12T fuse, and we can see that the 12T fuse spends most of its time in the sweet spot between the two fuses, but up here, around 20, 30, 40, around 50 seconds, well, actually closer to 40 seconds, you get into this spot where the transformer could be damaged and the fuse doesn't operate. So again, not ideal. For this little stub here, for these conditions here, if you ever get into the big overload, the high impedance fault where you don't have a really good connection, but you still got too much current flowing, you could cook this transformer and the 12T fuse would be happy to just sit there and not do anything about it. The 8T fuse, on the other hand, is perfect. It sits entirely in between those two lines in our protection margin from top to bottom. And so for this transformer, the 8T fuse would be the perfect one. Thanks so much. I hope you've enjoyed it. Please give the homework a shot and look forward to